My student. So in our previous lab, we have discussed the steps of designing a low pass filter. Okay, how to calculate the elements value of the low pass filter. Okay, so here we will consider one example, and we will try to design low pass filter for a given specification. Okay, that is what we exactly discussed in our previous lab session. So here we are given some specification. Okay, so we have to design a low pass filter for this specification. Okay, okay. So the filter type is Chebyshev flush type filter. Okay, and there are some specification given: pass band cutoff frequency, stop band edge frequency, so on. Okay, so if we draw a filter response, it will look like this. Okay, so I'm drawing the filter response is for this given parameters. Okay, so if we draw the filter response, okay, actually in filter response we are going to draw the gain of the filter in dB. Okay, and for different frequencies. Okay, for difference omega. Okay, so these are frequency radian per second. Okay, so you know that this is the power gain. Actually this is power gain. Okay, so you know that filter is a two-port device. Okay, filter is a two-port device like this. Okay, it has two port. This will be port 1. This will be port 2. Okay, and so let's say that the input voltage is A1, and there can be a reflected voltage. So this will be A1, and let's say that it is B1. Okay, in the second port, the input signal is A2, and the output voltage is V2. Okay, so I have marked the voltage value, input, output, and reflected voltage values. Okay, so this diagram is very familiar to us. Okay, when we are learning about two ports network parameters, we have gone across this diagram many times, I hope. Okay, so what is the gain here? What is the gain? Normally gain is defined as V out, output voltage, divided by input voltage. This is the voltage gain. Okay, this is the voltage gain. Okay, so in this case the input voltage is A1 and the output voltage is B2. So in this case it will be B2 divided by A1. Okay, so this is the voltage gain. Okay, and what is the power gain? If we want to get the power gain, what is that? Okay, so we know that if we get the so this voltage may be complex. Okay, it has a magnitude and a phase also. These are complex values, these voltages are. So if we get the magnitude and square it, then this will be our, so we have to get the magnitude of the voltage and square it, then this will be our power gain. Okay, we have learned this. Okay, so we can write it like this: V out, V in, magnitude square. Okay, so this is the power gain. Okay, so normally this power gain is expressed in dB. Okay, so if we put the 10 log 10, okay, so power gain in dB, okay, this will be 10 log 10, this V out V in, okay, V out V in, and square. So I can get the square out. Okay, so it will be 20 log 10 magnitude of V out divided by V in. Correct? Okay. In our case, it will be 20 log V2 divided by A1. Okay. So this is the power gain. Actually, we are going to plot the power gain of the filter. Okay, of the Chebyshev filter. And here you can see that this filter is a passive device. Okay, so V out should be always, so this is a passive device. Okay, we know that this is a passive device. So V out should be less than, maybe equal to V in. Okay, it should be less than or equal to V in. Okay, because this is a passive device. There is no any amplification. There should be attenuation. Okay, so you can see that this power gain, so this V out will always lower than the B2 is lower than the A1. So here you will get some fractional value, rational value. Okay, so always this power gain will be a minus value. Okay, so this power gain will lie on 0 to minus value. Okay, minus values. Okay, 0 to minus values. Okay, but if this is amplification, the gain should be plus, no, because V out is normally greater than the V in. Okay, so that is the power gain. And also, if you want to calculate the attenuation, okay, so you can see that here we are given the attenuation. We are given the attenuation, stop band attenuation. Okay, stop band attenuation, and okay, that is, so we are given attenuation, not gains. Okay, so how this attenuation and gains are related, you already know that. Okay, so you already know that if we get the minus, so this is the gain. Okay, the actual attenuation is the reciprocal, no, of the, not reciprocal, the out of the attenuation is actually V in divided by V out. Okay, so this is the attenuation. Okay, so if it is in dB, if you get the minus value, okay, if you get the minus value, okay, so if you get the minus power gain in dB, so this will be the attenuation. This will be the attenuation in dB. Okay. Okay, I think already you have this idea. Okay. So you can see that for a passive device, attenuation should be always greater than the, 1, greater than 1, because there is attenuation. Okay, if the attenuation is high, V out should be low, very low. If the attenuation is high, V out should be low. Okay, so when the attenuation is increasing, this V out will be getting low. Okay, if the V out is getting low, attenuation will be increasing. Okay, so the attenuation should be in plus value. Okay, so you can note that here it is plus 30 dB. Okay, so if the gain, if you want to find the gain here at this point, it will be minus 30 dB. That is the power gain. Okay, now we are going to draw the gain. Okay, actually you can draw the attenuation also, no issue. Okay, but I am familiar with the gain plot. Okay, gain response. Okay, so I will draw the gain plot. It will look like this. Okay, so here we have 0. Okay, So this gain will not exceed the zero. Okay, it is always below the zero in minus direction. Okay, so these are minus value. Okay, and you can see that maximum passband ripple. Actually, this is also given the attenuation. Okay, 0.3 dB. Okay, plus, but if we are mark it in gain graph, it should be minus 30 minus 0.3 dB. Okay, so it will be minus 0.3 dB. Okay, because this is a gain and this is attenuation, and I am marking the gain. Okay, so I have already told you that the attenuation is minus gain. Okay, or the gain is attenuation minus attenuation. Both are correct, no? Okay, so this is minus 3 dB. Okay, and we have the ripple here like this. Okay, okay. So this is Chebyshev one type uh, filter. Okay, so only ripples are in the pass band. Okay, ripples are in the pass band. There are no any ripple in the stop bands. Okay, so this will go like this. Okay, this will go like this. Okay, and you are given the stop band H, sorry, pass band H frequency. That is also we called as cutoff frequency for the Chebyshev filter. Okay, so here this will be the cutoff frequency. It is 5.8 gigahertz. Okay, so so I will I will draw it with hertz. Okay, I think it is easy. Okay, now I will draw it with omega. Okay, so so you have to convert hertz to radian per second. For that you can multiply by 2.5. Okay, so it is 5.6 gigahertz. Okay, 5.6, 5.8 gigahertz. Okay, so here I will put 10 to the point 0.9. Okay, so I can write like this 5.8. Okay, 25, 5.8. Okay, so this will be our pass band H frequency. Okay, if this is a Butterworth filter, this pass band H frequency and cutoff frequency are different. Okay, for a Butterworth filter, normally the cutoff frequency will be the 3 dB frequency. Okay, so it is somewhere here at the minus 3 dB gain. Okay, but in the case of Chebyshev filter, this cutoff frequency and pass band H frequency are same. In other words, we are not talking about a cutoff frequency or 3 dB frequency in Chebyshev type filter. But for the Butterworth filter, that is a significant parameter. Okay, so this will be our pass band H frequency FP. Okay, I will write it as omega p. Okay, okay, so this will be omega p. Okay, pass band H angular frequency. Okay, and you can see that here we are given another stop band H frequency, and it is 7.2 gigahertz. So that means it is somewhere here. It may be here. Okay, and that is 257.2. Okay, and it is called stop band frequency, Fs. Okay, so I will write it as omega s. Okay, okay, and it is said that the minimum stop band attenuation should be 30 dB. That means What is that means? It means that we are given a stop band. Okay, it is beyond our edge frequency, pass band edge frequency. Okay, so our the given stop band frequency is greater than our pass band edge frequency, and it is said that for this frequency, attenuation should be greater than 30 dB. Attenuation should be greater than 30 dB. What's that means actually? Okay, it should be greater than. So the minimum will be 30 dB, no? For the attenuation should be greater than 30 dB. Okay, for that means for this frequency Fs, the attenuation, the minimum attenuation should be at least 30 dB. Okay, so if it is high, it will be okay. So what's that means? That means that, okay, that means that after this point, so this response is somewhat like this. Okay, this response is there is a ripple, okay, in the pass band. That is because it is a first type one Chebyshev filter. Okay, and here it is given another frequency. Okay, and he said that this should be, the attenuation should be at least 30 dB. Okay, that means for this frequency the attenuation should be very high. That means if we are given this signal, it should be stopped. Okay, that is why the attenuation should be high. Okay, so this frequency should be stopped by the filter as much as possible. Okay, so that is why it is given the attenuation should be greater than 30 dB. In other words, attenuation should be at least 30 dB. Okay, so if it is, the attenuation is high, that is very good. Okay, so you should have at least the attenuation for 30 dB. Okay, that is the requirement. Okay, and when we deal with the gain, what's happened? Okay, so this attenuation is minus sign. Okay, minus sign. Okay, then if we are dealing with gains, that should be 30 dB, minus 30 dB gain. Okay, and when we are talking about the gain, what should happen? At this frequency, this gain should be less than. Okay, the gain should be, so here it is greater than. The attenuation should be greater than 30 dB, and here the gain should be less than minus 30 dB. Okay, gain should be less than minus 30 dB. Okay, so gain should be less than minus 30 dB. Okay, because this gain should be very low. If you are considering the gain for this one, it should be low. Okay, but if you are talking the attenuation for this point, it should be high. Okay, so if you are given the attenuation, always it is said that attenuation should be greater than. Okay, but if you are given gain, normally you will be given as the gain should be less than minus 30 dB or something. Okay, so don't get confused with these terms. Okay, so that the minimum stop band attenuation should be greater than minus 30 dB. Okay, so if we are considering the gain, it should be minus. Okay, so it should be minus 30 dB. Minus 30 dB. Okay, so this will be our response, filter response. Okay, this will be our filter response. Okay, and as I can remember, this filter response is given in frequency domain as like this. Okay, square should be divided by 1 sine square square only. Okay, and this is called Chebyshev function. Chebyshev function. Okay, there is a expression for this Chebyshev function also. It is a function of omega. It is a function of frequency. Okay, and this epsilon is called called as ripple factor. This will be the ripple factor. Okay, so so normally for I'm not very much sure about this expression. I just write it as I can remember it. Okay, so there may be some parts missing. Okay, anyway, you can please check. Okay, please check and get confirmed. Okay, so for a power gain, this kind of expression will be there, and this will be expressed in dB. Okay, so this will be expressed in dB. Normally we put 10 to the power log 10 for this one. Okay, in dB. Okay, so that is what we exactly doing here. Okay, so this will be our expected response. Okay, so this will be our expected response of the filter. Expected response of the filter. Okay, so once you have complete the filter, you have to check you will get this response. If you can get this response, your filter design is okay. Okay, otherwise you have to do some adjustment. Okay, so that is the idea. Okay, so this will be our expected response. Okay, and how to find the expected response actually? Okay, so you can simulate it, you can measure the gain. How to measure the gain? So very easily you can do that. If you have come to the first lab session, physical lab session, I think you will get a good idea about this. Okay, but none of you have, only one student is there, was there. Okay, uh, so you can see, if you, so here this is the power gain, this is what we have plot. Okay, so you can see that. I will write it here again. Power gain in dB is equal to 20 log square of V out V in. So this is what we have plot here. Okay, so we have plot this one. Okay, so in our case it will be PG dB. Okay, so if I put this value according to my diagram, okay, according to this diagram, okay, according to this diagram, okay, it will be 20 log, the V out is B2 and V in is A1. Okay, so what is this value? What is this value? These are voltage. What is this value? Okay, so you know that if I write the B2 using the S parameters, it will be S21 A1 plus S22 B2. Okay, so how we are measuring this parameter? Okay, we have discussed this in our first lab session, and we use the network analyzer to measure the S parameters. Okay, so how to measure this? Okay, so you can match this output. Okay, you can match this output with the match load. Okay, so A2 will be 0. There will be no any reflected voltage in this port. So this A2 will be 0 if you match this side. Okay, so this will be A2. Okay, this is A2. Okay, this is A2. Okay, so this A2 will be 0. Okay, so you can get that S21 is equal to B2 divided by A1. Okay, so when A2 is 0. Okay, actually this is how we measure the S21 parameter. Okay, how we measure the S2 parameter? We set A2 as 0 and we measure the B2 divided by A1, output voltage divided by input voltage. Okay, so if you get the magnitude of this S parameter, so these S parameters are also complex. if you get the magnitude, okay, so it will be magnitude of B2 divided by A1. That is exactly this one. Okay, so this will be magnitude S21. Okay, so you can understand that. Okay, so once you have calculate the elements value, okay, you can design or you can simulate this filter in a high frequency simulation software. Okay, high simulation software. Okay, so you will get this kind of if I use the lumped element, okay, you will get this kind of circuit. Okay, you will get this kind of circuit. For your low pass filter, this kind of ladder circuit you will get. Okay, you will get this kind of ladder circuit. Okay, okay. So these elements can be changed. Okay, actually in this response there is a value for this n. Okay, so you can see that here n is there. Okay, so this n is the filter order. Okay, we know that it is that n is the filter order. Okay, this n, we have discussed this in our labs. Okay, this is filter order. Okay, and this filter order will give you the elements value, the number of elements. So there are capacitance and inductance. Okay, so these are farad and these are measured in Henry. Okay, so these are capacitance and inductors. Okay, so filter order will give you the number of capacitance and inductance. So here it will be 1 2 3 4 5. So filter order for this case will be 5. Okay, so you will get this kind of circuit for your LPF design. Okay, so how you can justify this as a low pass filter? Okay, how can you justify this as a low pass filter? Indeed we can. Okay, so you can see that if we input DC value, okay, this capacitor will block the DC and this inductor will not block the DC, and DC value will be available in this port also. Okay, but if you plot the high frequency, okay, AC voltage or AC signal, this inductor will pass the AC signal. So that will pass the AC signal, and this this capacitor will pass the AC signal, but this inductor will block it. Okay, so here the AC signal will not be available here. Okay, so you can see that if we can carefully calculate this capacitance and inductance value, you can completely block some low voltage, you can let pass the low frequencies, and you can stop the high frequencies. Okay, if you have calculate these values carefully. Okay, so that is the idea. Okay, so once you have decided this kind of ladder circuit, okay, so if you have a software for a high frequency to simulate, you can simulate this circuit. Okay, okay, and you can measure the S21 parameter, and you can get the magnitude of S21 parameter in dB. Okay, so this should be your filter response. No, this should be your filter response. That is what I want to tell you. This will be your filter response. Okay, so this assignment or this lab will expect, okay, this comparison actually. Okay, so here you have to implement this filter as a step filter. Okay, step impedance filter. Okay, so that you will get some transmission line like this. Okay, you will get some transmission like this. Okay, and you can uh, calculate the filter. Okay, you can calculate the filter, you can make the filter. Okay, and you can simulate this in HFSS. Okay, so after you draw this circuit in HFSS, you can measure the S21 parameters in dB, and you can compare it with this expected value, expected response. You can compare it with this expected response, and you can come to a conclusion whether your design is okay or not. If it is not okay, you have to give some solution how to fix this. Okay, so that is the idea, that is the task you have to done in your assignments. Okay. Um, okay, so we will see how to do this. Okay, so now actually we will start our filter design. Okay,